This is a continuation of problem session for section 5, or chapter 5. I'll address here something from page 134. Let us consider problem 6 from page 134. In this problem, one considers the field Q of X. Q is the field of rational numbers over the polynomial x squared minus 2. So x squared minus 2 is irreducible in this ring of polynomials with rational coefficients, Q rationals. It is irreducible because it is a polynomial of degree 2, and it has no roots, no rational number squared is 2, as we all know. So, first of all, there is a claim that about the set Q of this thing, because first of all, because the polynomial is irreducible, therefore x squared, therefore Q of x over x squared minus 2 is a field. As we know by theorem 5.10. So this is a field, and as a set, this is a set of congruence classes of polynomials modulo this polynomial. Every congruence class, so Q of x over x squared minus 2 is, as a set, as a set is the set of congruence classes. Of polynomials modulo this polynomial. And every congruence class, as the book claims, can be written as the class of a linear polynomial ax plus b, a polynomial of degree 1, with rationals a and b. Now, the book asks why this is the case. That is because for every polynomial, with rational coefficients, by Euclid's lemma, or as the book calls it, by division algorithm, we can write f as q x squared minus 2, q times x squared minus 2 plus a remainder, with q a polynomial with rational coefficients, and the remainder is 0 in the field. 0 in this field, in the field of rationals, is nothing but number 0, or degree of the remainder is smaller than the degree of this polynomial, x squared minus 2, which is 2. The set of possible remainders thus as 0 and all polynomials of degree smaller than 2 means 0 and 1. So possible remainders is the set of 0 and polynomials of degrees 0 and 1, which is, of course, all ax plus b for various a and b rational numbers. We get 0 if both a and b are zeros. We get polynomials of degree 0 if a is 0 while b is not. And these are constants, non-zero constants, and we get polynomials of degree 1 as soon as a is not 0. Now we have that f, so thus every polynomial is congruent to a polynomial of this form. Thus, for every polynomial, we have that f is congruent to ax plus b, some polynomial of this form, the remainder from division by x squared minus 2, which translates to whatever class we take with some any representative f is the same as the class of some polynomial of this form with some rational a and b. At the same time, two different polynomials of this form cannot be congruent. Two different polynomials of the form ax plus b, where a and b are different, they're two different things, cannot be congruent modulo x squared minus 2, because their difference has a degree which is zero or 1, and as such cannot be divisible by a polynomial of degree 2. This polynomial has degree 2. Polynomial of smaller degree cannot be divisible by a polynomial of bigger degree. We know that degrees add up when we multiply polynomials. So thus, we're just justified, as the book asks us to do in this collection of exercises, why, as a set, this is exactly this one. So as a set, this is exactly this set. Now the book asks us to describe addition and multiplication in this field using the presentation of the field with this set. Let us describe addition and multiplication. So Oh yes, so possible remainders are those, and as a set, this is the set of classes of these remainders. I wrote classes here, I did not there because that was all possible remainders. So now this set is the set of classes. Every remainder is a representative of its class, all polynomials congruent to this remainder modulo x squared minus 2. The addition is easy. Two classes add, when according to our rule we simply add representatives, and this is the class of the sum so the class of sum of representatives, which is a plus c x plus b plus d. So out of these two classes we produced another class, and that's the end of the story. The class of this polynomial, whether it is 0 or non-zero, no more, no higher degree, if not 0, than 1. It is a little bit tricky with multiplication. When we multiply two classes, we, of course, again, by the rule, get the class of product of representatives. That is the class of ax plus b, cx plus d. And we can multiply them as two polynomials with rational coefficients. Nothing really tricky at this moment. We got ac x squared plus bc plus adx, or ad plus bc x plus bd. Now, however, it is correct, but we're out of the set. This polynomial, if neither a nor c is 0, this polynomial has degree 2 and is not in this set of polynomials or 0, polynomials of degree 0 and 1. This one has degree 2. So in this class, in the class of this product polynomial, we have to back choose a representative of this shape. How do we do that? Well, basically, it is along division. We subtract from this polynomial ac times x squared minus 2. With this subtraction, we don't change the class. We are still in the same class. The difference between the two polynomials is going to be divisible by x squared minus 2, a multiple of x squared minus 2, ac times x squared minus 2. So we are in the same class, but we will kill this first, the leading coefficient. And in this way, we will produce a representative of this same class, which has either does not have a degree or has a degree which does not exceed 1. let us do that. I subtract this polynomial, and what I get is still same thing, AD plus BC x. AC x squared cancels, and this BD stayed on its place, and we got extra 2AC. 2 plus 2AC appears here. We are done. So this is description of multiplication. The product of these two classes is equal to the class of this polynomial. So on this set, the operation of addition is this one. The operation of multiplication is this one. We multiply two classes, obtaining another class. So we've got an operations of addition and multiplication on this set. We know, because the polynomial is irreducible, what we produced is not just a ring, but a field. So we, in this field, where 0, so in the field, just let me write it down for you, in the field we have 0, which is just 0, is the class of 0. Meaning A and B are both zeros. And 1, call it F. Otherwise, I will have to write too complicated an index. This is the class of 1, of course, and you can easily check that that coincides with our operations. This is when A is 0 and B is 1. Number 1. These are two rational numbers. This is also number 0, two rational numbers. There is another representation of this field. In this same field, we have that x squared as 2, of course. So if we have x is the root of this polynomial, so x times x. What is x? X is 1 x plus 0. This is what x is. 1x times plus 0. So this is A, B, C is 1, D is 0. Let us calculate what happens. So this is A, B, C, D. A is 1, B is 0, C is 1, D is 0. So AD plus BC. AD 0, BC 0. 0 times x plus BD plus 2AC. BD, both zeros, is 0, and AC is 1. 2AC is 2. So this is the class of 2 after all. 0x plus 2. So x squared, that is x squared is 2, oh, still write it this way. What we found is that x squared is the class of 2 in this field. Now, their construction is parallel to the construction of complex numbers out of real numbers. But we started with rationals, not all reals. And we can, what we constructed is still only a subfield of real numbers, in fact, or is isomorphic to a subfield of real numbers, not even nearly all of them. Well, we can, so alternatively, one can write a root of 2 plus b instead of the class of ax plus b. Based on this calculation, the class of a rational number is still the class of this rational number. You can operate with them as rational numbers. This field contains a copy of Q. These are classes of rational numbers, the copy of this field, as we know. And we have an element of the field whose square is 2, a root of this equation. So we can denote this element by square root of 2. In this case, I'm not trying to really take a square root of 2 as a real number. I just denote it. So that rewriting is simply we denote it square root of 2 to be, instead of x, we wrote this thing instead of x because the square of this is 2. So you may, now it is easy and I leave it on you, check that our operations of addition and multiplication coincide with what you usually think about if you multiply and add these numbers. And you get a different description of this same set. So this is an alternative description which you may look at. So Q of x over x squared minus 2 is the set of, in this case, instead of this, we write this, a root of 2 plus b. A and b are rationals operating now with these as with real numbers, meaning all operate, or you operate as this one, taking into account that root of 2 is something which either you leave as a coefficient of rational with the rational number, or when you square, it gives you a 2, denoted by root of 2, the element whose square is 2. So this is an alternative possible description of this same field. You may chunk that using operating as real numbers, this is a field, and this becomes in this way a subfield of the field of real numbers. There is an ambiguity which I'm not going to discuss. Instead of root of 2 could be also negative root of 2. If you think about that as a real number, with negative root of 2, that's going to be a different real number. Still, everything holds true. So there are two different embeddings of this field into the field of real numbers. Doing it this or that way, you embed this field into the field of real numbers. Think about this as a subfield of the field of real numbers, but there are two different subfields of the field of real numbers. In a sense, actually this is the same subfield, but it has a non-trivial map into itself, taking root of 2 into negative root of 2. So two different ways to embed this field into the field of real numbers. The image is actually the same subfield of the field of real numbers. So that is about this example with some alternative description as well. So we finished here, and these were some extra remarks about this field and its relation to the fields you know, the field of real numbers. So, and some alternative description of this field, which will give you same operations of addition and multiplication. Here is another exercise from the same set 11 on page 134. They say that the ring R defined as Q of X polynomials with rational coefficients over X squared is not a field. That is actually what theorem 510 tells us immediately. X squared, that is not a field because X squared, a polynomial, is not irreducible. X squared is x times x. So it factors into a product of two identical polynomials of degree 1, x and x. The book asks this exercise as before theorem 5.10. So the book asks for a straightforward check that this is not a field. Let us do that. For that, we again using the concrete description. the description is similar to what we just did. So we write for the same with the same argument as a set of classes of x plus b I did not use the fact that x squared minus 2 was irreducible to write that in the previous problem. It was just a polynomial of degree 2. And addition is going to be the same. Multiplication of these classes now is different from the previous problem. This is, and I will only write multiplication. This is all problem 8 on page 134, which I don't want to do in full. I will do just what was different, the multiplication, what was substantially different from the previous problem, namely multiplication of these classes. So how do we multiply the classes? Let me write. We take ax again as previously. We take class x plus b, class a b cx plus d, and as previously we multiply representatives to get a c x squared plus ad plus bcx plus bd, and again we produced a polynomial which is a quadratic in general. If a times c is not 0, we want a linear polynomial. We want to get rid of this term. We want a linear polynomial in the same class. This is the class of this quadratic polynomial. For that, we do long division by x squared, or simply subtract ac x squared. The two polynomials are going to be congruent modulo x squared, so belong to the same class, and what we produce is ad plus bcx plus bd. So this is the multiplication in this ring. I want to say that, after all, it is not a field. How it is not a field? We take, well, R is not a field. We know that a field must be integral domain. So what I prove is not even an integral domain. Every field is an integral domain. Not every integral domain is a field. Integers is an example of integral domain, which is not a field. Here, not even an integral domain, therefore not a field. For that, I want to show that a product of two non-zero elements is going to be 0. That would suffice. So I take the product of two non-zero elements, namely x and x. This is x is ax plus b, 1 x plus 0, 1 x plus 0. And meaning A1, B0, C1, D0. And I calculate this according to this formula for multiplication. Which class do I obtain? AD plus BC. AD 1 times 0, 0. BC 0 plus times 1 is 0. So this is 0 times x. Plus BD 0 times 0, 0. Which is the class of 0. Oh, in this ring, it is easy to see that 0, A equals B equals 0, is the 0 in the ring. So, and this x is not 0, so while x is different from 0, x times x is 0. Therefore, I justified R is not even an integral domain. So that was problem 11 from the book. So though this R is actually a commutative ring with identity, an alternative description of R, you may describe a possible alternative description of R. You may say that these are just ordered pairs A, B. So you think about that as just A and B. The fact that it is written as AX plus B doesn't matter. All information is contained in two rational numbers, A and B. They, as an ordered pair, determine the whole thing, the class. And we know how to multiply these classes. We, of course, easily know how to add them. So R, from this perspective, is the set of ordered pairs A and B as the set with addition and multiplication given with operations so A, B plus C, D is the pair A plus C, B plus D, and multiplication AB times CD is given in this way: AD plus BC, BD. With this operation, this is a ring, as we know, because we know that this is nothing but an alternative description of this ring. So this is a ring. A commutative, you can see it easily from the symmetry of this multiplication. And so in this ring, the role of 0 is played by the pair 0, 0. Identity is here easy to check with these operations, that this is a 0 and this is identity. Again, check that multiplying using this rule by this element will not change the element you multiply by. Note that identity is different from 0 in this ring. So, and our 0 divisor, so this is, so R is a commutative ring with identity not an integral domain. 0 divisor, which we found, is the following. This is 1, 0. 1, 0 times 1, 0. The element is different from 0, 0, so it is not 0. And with this operation, you can easily check AD plus BC, 0 plus 0 is 0, and BD is 0, 0 times 0 is 0. So, in this way, you got an alternative description of this ring R. Still, R it was originally Q of X modulo X squared. Polynomials with rational coefficients modulo this polynomial. So, what we produced is a commutative ring with identity, so the set of ordered pairs with these operations with a 0 divisor. Right, I will pass to exercises from next section in the next fragment. Thank you for listening.